Hello, welcome to the lecture for section 7.1, solving trigonometric equations with identities. All right, let's begin by solving a basic algebra equation. Here's a quadratic equation, 2x squared plus x equals 0, right? To solve this, probably the easiest way to solve this would be to factor out the x. All right, so when I do that, I'm left with a 2x plus 1 equals 0. So x times 2x plus 1 equals 0. Then I can employ the zero product principle, and I can say either x equals 0, or I can say that 2x plus 1 equals 0, right? Solving for x, just subtract that 1 from both sides, and then divide by 2, and we see our second solution for this quadratic equation is x equals negative 1/2, right? So we have two solutions here, x equals 0, x equals negative 1/2. Well, that same technique can work very nicely for trigonometric equations that are quadratic in nature, right? Quadratic in nature. So take a look at this trig equation over here, 2 times sine squared of t plus sine t equals 0. And we always need to know how many solutions, or if we're looking for all solutions, or in this case, we just want solutions that are once around the unit circle, right? Between 0 and 2 pi. All right. Well, if I consider, sometimes we call this maybe doing a u substitution, right? So if I say I let u equal the sine of t, right, and make that u substitution into the equation, then I'll have 2u squared plus u equals 0. And look at that, it's the same equation that we were solving over here for x, right? We would factor out the u. We'd be left with a 2u plus 1 equals 0, right? Then employing the zero product principle, we see that either u equals 0 or 2u plus 1 equals 0. Solving the second equation for u means subtracting 1 and dividing by 2. So u then has to equal negative 1/2. All right, same solutions we received in the quadratic equation over here, but I've made this u substitution. Now I need to undo that u substitution. So, because I want to solve in this trig equation, I want to solve for t, right? Not u. So let's undo it. If u equals 0, then I can say that the sine of t equals 0, right? And solving for t means take the inverse sine of both sides, right? So sine negative 1 of the sine t equals sine negative 1, or inverse sine of 0, right? The inverse sine undoes the sine, so t then is going to be the inverse sine of 0, or the angle, right, who has a sine of 0, right? Well, this one's on the unit circle, so we can take a look at the unit circle. Where is the sine equal to 0? The sine correlates to the y-coordinate of the terminal point, right? So we see that the y-coordinate of the terminal point, there's a sine of 0 right there. X is 1, y is 0. Do we have another case and once around the unit circle? We do. Here's another y equals 0. So the two solutions that we have here are 0 radians or pi radians. We're dealing with radians. All right. So let's go back to our problem here then. 0 is good because 0 is less than or equal to. So my two solutions here in this first equation for t are going to be 0 or pi. All right, because that's where our y-coordinate is 0. Now we have this other one to solve, though. We have this other equation over here where u is equal to negative 1/2. So let's undo that u substitution. So then we'll say the sine of t is equal to negative 1/2. Inverse sine of both sides tells us that t is the inverse sine of negative 1/2, or the angle that has a sine of negative 1/2. This one's also on the unit circle, so we won't need to bother with the calculator. Let's just go to the unit circle. Where do we have a sine of negative 1/2? Where is our y-coordinate of the terminal point, negative 1/2? Well, let's see. Why is there negative down below the horizontal axis? So I'll look down below here, and I see there is a y of negative 1/2 right there. and there's another one right here. So I have two solutions, and once around the unit circle anyway, 7 pi over 6 and 11 pi over 6. Right? So my two solutions here are 7 pi over 6, 11 pi over 6. So in total here, there are 4 solutions for t that satisfy this equation. Okay? Sometimes we need to use identities to solve trig equations, right? It's very hard to solve a trig equation that has multiple trig functions in it. So these identities can help us to rewrite the equation with only one trig function, like only the sine or only the cosine. We usually try to make them be, we usually try to convert equations to sine and cosine. That's a technique that often is helpful. Okay, so let's look at another example where we will use some of these basic identities that we've already been working with. All right, in this trig equation here, we have 3 times the secant squared of t minus 5 times the secant of t minus 2 equals 0. All right. Now, if you look at that, you'll note that that's quadratic form, right? We have a squared term to the first power term and a constant term. It's a nice format for a quadratic form. So I think a substitution can be valuable here to start with. All right, so let's let u equal the secant of t, all right, and rewrite this equation with u. So then we'll have 3u squared minus 5u minus 2 equal to 0. And that's a fairly basic quadratic equation. This one can be solved by factoring as well. We won't need the quadratic formula here. Let's see, when we factor that, that's going to factor into there, 3u plus 1 times u minus 2, right? Because negative 6u and positive 1u is negative 5u. All right, so there's the factors. Now we can do the zero product principle here, and we say that 3u plus 1 equals 0, or u minus 2 equals 0. All right, solving for u here, let's see, we would subtract 1 from both sides and divide by 3. So u would be negative 1/3. Here, just add that 2 to both sides, and u equals 2. All right, let's undo this u substitution. All right, for the first one over here, u equals negative 1/3. We're going to put the secant back in there, and we're going to say the secant of t equals negative 1/3. All right. Well, I don't have an inverse secant function on my calculator to solve for t here, but I do know that there's an identity that tells me that the secant is equal. Let's see, where can I write that? It's right up here. There's an identity that tells me that the secant of some angle is equal to 1 over the cosine of that angle. Right? So I want to go ahead and make that substitution here. Instead of secant of t, I'm going to write this as 1 over the cosine of t equal to negative 1/2. Right? I guess I maybe should have written it here to show that was my reason. That's okay. Then I just want to solve for the cosine of t, right? Let's see, if I multiply both sides by the cosine of t, I'll have negative cosine, and then multiply both sides by 2, or by negative 2, I'll have, well, let's do each step here. All right, we'll start by multiplying both sides by negative 2. Right, so that'll all divide out. So we'll have 1 equal to negative 2 over the cosine of t. Then I'll multiply both sides by the cosine of t. Okay, and I'll see that the cosine of t is equal to negative 2. Right? Now, can that ever happen? Can we ever get a cosine that's equal to negative 2? No, that's not in the range of the cosine, right? Without transformations, the cosine oscillates between negative 1 and positive 1. So what does that mean here? Well, that means that this particular function, did I do something wrong here? Wait a minute. I don't think so. This particular function is not having a negative 1/3. Oh, why did I do this? I did make a mistake here. I switched my negative 1/3 to negative 1/2. Do not know why I did that. Let's fix that. Thought something was wrong. Let's fix all these. There we go. All right. Okay. All right. So when I redo this, I see the cosine of t would be equal to -3, which of course also can't happen. Can never happen. So this is an invalid solution, right? This is an invalid solution. I have to throw this away. It's an extraneous solution, one that can't be. So that one's not right. Let's go, or can't, we have to throw that one out. That's not a true solution. Let's go over here and look at the second one though. Let's undo that u. So we'll say that the secant of t is equal to 2 here, all right? And again, let's use that identity that the secant is equal to 1 over the cosine. Make that substitution. So I'll say that 1 over the cosine of t is equal to 2, okay? Multiply both sides by the cosine of t and then divide by 2. And I'll see that 1/2 is equal to the cosine of t, all right? This looks like a more legitimate cosine. In fact, it's 1/2. It's going to be on the unit circle. So if we take a look at the unit circle, where is the cosine 1/2? Cosine correlates to the x-coordinate. So x's are positive in quadrants 1 and 4. So where do we see a positive x-coordinate of 1/2? Right there at pi over 3. But we're going to have another one down here. There it is, at 5 pi over 3. So I have two solutions there. The inverse cosine of both. So t is going to be either pi over 3 or 5 pi over 3. Okay. This particular equation only had 2 solutions instead of 4, even though it's quadratic in nature. But we had to throw this guy out. It violates the domain. Or the range, I'm sorry, violates the range of the cosine. All right. So let's look at another type of equation. I mentioned earlier, it's easier to solve trig equations when they're written with only one trig function. It's usually better to have it either be cosine or sine, right? If we look at this equation here, 2 sine squared of t equals 3 cosine of t. I have 2 different trig equations there, so I want to make some substitutions. I want to use identities to make substitutions so they're all written with the same trig function. All right, we've worked with the Pythagorean identity before. It's a very valuable identity. In its base form, sine squared plus cosine squared equals, that's a typo, equals 1. All right, but if we rearrange that, we could say that sine squared is equal to 1 minus cosine squared, or cosine squared equals equal to 1 minus sine squared. All right, well, I like this version of the Pythagorean identity here because I've got a sine squared. If I make that substitution, I'm going to convert that sine squared into 1 minus cosine squared. Then I'll have an equation with just cosines in it. All right, so let's go ahead and rewrite that. Instead of 2 times the sine squared, I'm going to say 2 times 1 minus the cosine squared of theta. I make that substitution there for sine squared, right? It's going to be equal to 3 times the cosine. Oh, I'm not using theta, sorry. It's supposed to be t. Let's put t in there. Okay, equals 3 times the cosine of t. All right, let's see. Let's simplify and rearrange this equation a little bit. If we distribute that 2, we'll have 2 minus cosine squared of t, 2 minus 2 times cosine squared of t, there, is equal to 3 times the cosine of t. All right, this is looking quadratic in nature, isn't it? So let's move all the terms over to the right-hand side, because for quadratic equations, we always want to set them equal to 0 to solve, right? All right, so we'll subtract 2 and add 2 cosine squared of t to both sides. we'll have 0 equal 2 cosine squared of t plus 3 cosine of t minus 2. Let's see if I got my signs right. Yeah. All right, now we can do that u substitution, right? If u is equal to the cosine of t, I could solve this equation for u. It would then become 2u squared plus 3u minus 2. Let's see, is that one going to factor? Yeah, I think I can factor that. 0, 2u and u, and then we'll say plus 2 here and minus 1 there. All right, so that's our factored version. All right, so the zero product principle then tells us that 2u minus 1 equals 0, or u plus 2 equals 0. Right? Solving this first equation for u, we'll add 1 and divide both sides by 2. So u would be 1/2. And the second one over here, u is just going to be -2. All right, let's undo the substitution. I'll go over here to do it. So then the cosine of t equals 1/2. From the unit circle, let's go look at that. Where is the cosine 1/2? Oh, it's this pi over 3 and 5 pi over 3 again. All right, so inverse cosine of both sides tells us that t is going to be either pi over 3 or 5 pi over 3. All right, but then there's the second equation to solve. Cosine of t equals -2. Can that ever happen? No. That's violating the range of the cosine function, right? So, or if I tried to do inverse cosine of -2 in the calculator, it's going to give me a domain error, right? It's going to tell me that that doesn't work. So we have to throw that out as an extraneous solution, right? So this particular problem, again, it had just 2 solutions, pi over 3 and 5 pi over 3. All right, let's try one more, or maybe 2 more. All right. Yeah, this one was just, we were doing once around the unit circle here, but on this next problem, we're going to find all solutions. I'm going to find all solutions on these two. All right, so looking at this first equation, I have 2 different trig functions again. That's not good. I have a secant and a cosecant. I'm sorry, a secant and a cosine. Okay, but if I remember that the identity, that the secant of theta is 1 over the cosine of theta, that's going to be a nice substitution here. Let me rewrite this equation. I can then say 1 over the cosine of theta is equal to 2 times the cosine of theta, right? Let's do some rearranging here. I don't like cosine in the denominator, so let's multiply both sides by the cosine of theta. And we have 1 equals 2 times the cosine squared of theta. All right, continuing to solve, I could do a u substitution, but I don't know that I really need to here. Continuing to solve, let me just divide both sides by 2 and then take the square root of both sides, right? So then I'll have that the cosine of theta is positive or negative the square root of 1/2. Okay, and I can write that a little bit better. I can say the cosine of theta is equal to either positive or negative. Let's see, that'd be 1 over the square root of 2, since the square root of 1 is just 1. And if I rationalize that denominator, it's going to be positive or negative square root 2 over 2. Right? Multiply both sides by square root 2 over 2. Okay, so there's my solutions, either positive or negative square root 2 over 2 for the cosine of theta, right? So, and again, I could do inverse cosine with my calculator, get decimal approximation, but I remember that this is on the unit circle, so it's probably better to choose an exact answer. Where is my cosine going to be positive or negative square root 2 over 2, right? Well, cosine is our x-coordinate, right? So there's 1, pi over 4. There's a negative, 3 pi over 4. Okay, what else do I have? Square root 2 over 2, cosine, there's 1. There's a negative. Okay, that's 5 pi over 4. And here's a positive 7 pi over 4, right? So once around the unit circle has these 4 solutions, right? It has these 4 solutions. I could say pi over 4, what were they again? Pi over 4, 3 pi over 4, 5, and 7, right? Pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4, right? So, I mean, I could then just say it's pi over 4 plus, you know, maybe 2 pi times k, where k is any positive or negative number, integer number, right? Because that'll give me my multiple times around the unit circle. And I could do it for each of these. I could, but I could do it in here, I'll just write them. I could do that. Oops. Plus 2 pi k and then plus 2 pi k. But I've got some redundancy here, right? Because look, pi over 4 is just, or I'm sorry, 3 pi over 4 is pi over 4 plus pi over, oh wait, I said that wrong. Pi over 2. It's pi over 4 plus pi over 2, right? And then 5 pi over 4 is just pi plus pi over 4, right? And 3 pi over, or 7 pi over 4 is pi times 3 pi over 4 plus pi. Blech, I can't talk today. So I could simplify this, right? I could do this, or I could just write 2 things. I could say it's pi over 4 plus pi k, right? Since 5 pi over 4 is pi over 4 plus pi, right? And the other thing I could do then is I could say that it's 3 pi over 4 plus pi k, right? So that's a simplified version of saying it. I don't care if you write it this way, but in my open math, you might see that there's only an opportunity to put in 2 solutions, and it's in a problem like this, and that would be because there's a simpler way to write the same answer. Okay? Let's try one more. All right, find all solutions to cosine squared of, I think that's called phi, right? Phi. Cosine squared of phi equals -6 times the sine of phi. Here, we're only going to do it once around the unit circle. All right? Well, we're going to need to make a substitution here because we've got 2 different trig functions, right? And we know from rearranging the Pythagorean identity, let's see if I can find where I wrote that, there it is, that sine squared is 1 minus cosine squared, and cosine squared is 1 minus sine squared, right? So I think I'm going to convert this cosine squared to a sine, right? Because I know that cosine squared of some angle is 1 minus sine squared of that angle by the Pythagorean identity. So we'll make that substitution. We'll just say 1 minus sine squared of phi is equal to -6 times the sine of phi. All right. Now it looks quadratic in nature, right? So let's set it equal to 0. So we'll say 0. Let's see, we'll add the sine squared to both sides. So 0 is going to be equal to sine squared of phi minus 6 sine of phi, and then we'll subtract that 1 from both sides. Okay, now I can do the u substitution. We'll let u equal the sine of phi. Okay, so then 0 equals u squared minus 6u minus 1. All right, this is not going to factor. Nope. So to solve for u, I'm going to have to use the quadratic formula here, aren't I? Let's do it over here. All right, so the quadratic formula is -b. So we're going to say u is equal to -b. That would be negative of -6 plus or minus the square root of b squared. Right? So that'll be -6 squared minus 4ac. So that's minus 4 times a. A is just 1. C is -1. All right, then all over 2a. That's just 2 times 1. All right, so when we simplify that, we get 2 solutions here for u. Right? When we simplify that, we get 6 minus the square root of 40 over 2. And we also get 6 plus the square root of 40 over 2. Two solutions for u that we'll need to undo to solve for phi. Now, I could simplify this further, right? I could just simplify that radical to 2 square roots of 10, then divide out the 2's. But ultimately, I think I'm going to need to find a decimal approximation in my calculator, right? So I might not bother, or maybe I'll do it for fun, just for fun. Let's see, when I simplify this, that becomes, it becomes 6 minus, and the square root of 40 simplifies to 2 square roots of 10, right? So then I can just divide 2 out of everything, and this will be 3 minus the square root of 10 and 3 plus the square root of 10. Again, not really necessary here because I'm going to have to put this in my calculator to find a decimal approximation at some point. Actually, I could probably undo. Let's undo the substitution first. All right. So I've got two solutions here. The sine of phi is going to be equal to either 3 minus the square root of 10, right? Or the sine of phi is equal to 3 plus the square root of 10. So inverse sine of both sides will tell us that phi is equal to the inverse sine of 3 minus the square root of 10, or phi is equal to the inverse sine of 3 plus the square root of 10. All right, now let's go ahead and put this in the calculator and see what they are. All right, the inverse sine, oops. So inverse sine, that's second sine, there it is, inverse sine of, and we'll do 3 minus the square root of 10. Okay, there's our decimal approximation for that. It's negative, oops, 0.16 more. Let me get the rest. Lots of decimals. I'll say 1630. I'm going to do 4 decimals here. So negative 0.1630. All right, now we have to figure out the second one. So that's going to be the inverse sine of 3 plus the square root of 10. Maybe I'll just do this. So retype the whole thing entry, and then I'll just go back and change that minus to a plus. There we go. Plus. Okay. I can hit enter, and then I can see that decimal approximation. Oh, now why is it having a problem with that, do you think? There's a domain error. Right? Well, what is 3 plus the square root of 10? Right? What is that? Let's see. It's frozen a little bit here. It's some value that's going to be larger than 1, isn't it? Let's quit. And let's see what it is. 3 plus the square root of 10. Look at that. It's 6.16 more decimals. So that's no good. We have to throw that out. Violates the domain of the sign. All right, but here's the good answer. All right, that's a good one. But we need to find all the solutions. All the solutions. Let me erase a little bit so I got a little bit more space to write up here. So let's make a sketch of our unit circle. All right, where would the sine be negative? Or where would the, I'm sorry, that's the angle, right? That's phi. So where is the angle negative 0.1630? Well, the angle negative 0.1630 is maybe about right there, right? We'll say that's it. But we don't want any negative angles. That's supposed to be a 1. Do we? We don't want any negative angles. We want angles that are only between 0 and 2 pi. So I'm going to need to convert this, right? I'm going to need to convert this. Now the sine here, let's see, the x-coordinate was something we don't really care about, but the sine was just 3 minus square root of 10, right? That was the sine, the y-coordinate. Where is it going to be 3 minus square root of 10 again over here. So then we know there's at least 2 angles, right? The x there is going to be negative of whatever it is over here, but the y will be the same, 3 minus the square root of 10. Let's see if I can write that better. 3 minus the square root of 10. There we go. All right. And so, whoops. So now what do I need to do to convert these angles? Well, I have to think about reference angles, right? I have to think about reference angles here. Now, this angle here is equivalent to this little angle over here, right? And I know that pi is right there. So this angle all the way around here that has 3 minus the square root of 10 is going to have to be pi plus this little angle, right? This little angle. Well, when we go in the negative direction like this, we have negative 0.1630, right? But it's equivalent in measure here, and we're going in the positive direction, right? So one angle then that we can identify here as a solution is going to be pi plus the 0.1630. Right? There's going to be one solution once around. All right. Now the second solution is the positive version of this negative 0.1630, which is what? All the way around and then stop here. Okay. Well, I think the easiest way to present that solution is 2 pi minus the 0.1630. All right. So there's the two solutions in between 0 and 2 pi for phi. All right. So that ends the lecture for section 7.1. As usual, let me know if you have questions. Send me an email.